Welcome to iTTV for Form 4 Chemistry. The title of this lesson, The Atomic Structure. We continue with our lesson on the structure of the atom. In the previous lesson, we looked at states of matter, boiling point, melting point. In this lesson, we want to look at the atom in a bit more detail. The historical development of the atomic models. Number 1, John Dalton, 1803. Characteristics. Matter are made up of tiny, indivisible particles. Particles cannot be created nor destroyed. So the history of the atomic model begins with John Dalton, and he said that you have the tiniest of all things, which he called a particle, and the key thing here is he said it cannot be destroyed or split into anything even smaller. J. Thomson, 1897. Characteristics. Discovered electrons. An atom consists of a spherical cloud of positive charge with negatively charged electrons scattered around the sphere. So we move on from Dalton to Thomson. The biggest change here was the discovery of the electron. So we are adding the electron, which contains a negative charge, to our atomic model. Ernest Rutherford, 1911. Characteristics. Atoms are spherical and contain a positively charged center known as the nucleus. Almost the entire mass of the atom is concentrated at the center, which is very small. Most parts of the atom are empty. So we move on now, and Ernest Rutherford, who followed Thomson, has given us the positively charged nucleus. So we have a spherical shape, we have negatively charged electrons, and now a positively charged, tiny, very full of mass nucleus. Niels Bohr, 1913. Characteristics. Electrons move around the nucleus in fixed shells or orbits. Each shell is at a fixed distance from the nucleus. So now we move even further. Thomson's free-moving electrons now are actually in fixed shells. James Chadwick, 1932, discovered the presence of neutrons in the nucleus. A neutron is a neutral particle with its mass almost equal to a proton. So now we get the final part of our atomic model. That is the neutron. So the key things in an atomic model is we have a nucleus which is positively charged and contains neutrons, and around the nucleus in shells, orbits, we have the electrons moving around. Niels Bohr's model. The nucleus consists of protons and neutrons. The electrons move around the nucleus in orbits. The nucleus is positively charged due to the protons. And this is our modern day atomic model. A positively charged nucleus which contains protons and neutrons, and around it orbits in which electrons whiz around. The electrons are negatively charged. Number of protons equals number of electrons. Thus, the atom is neutral. And this is very important to remember. The atom is neutral because proton and electron numbers are the same. So if you had 20 protons, you could easily then answer a question by saying you also have 20 electrons. If I said to you I had 37 electrons, you would then know we would have 37 protons in that atom. Subatomic particles of an atom. Proton, electron, neutron. Now, these are the three subatomic particles. Please be clear about this word, subatomic. Whenever you hear it, it means we are referring to the pieces inside an atom, the proton, the neutron, and the electron. Each has got its own characteristics which you must know. It's a common question in examinations to ask you about the characteristics of the proton, neutron, and electron. So let's have a look at their characteristics one by one. Proton, symbol P, relative charge positive 1, relative mass 1 unit. So our proton has a charge of positive 1 and a mass of 1 unit. Now let's have a look at the neutron. Symbol N, relative charge 0, relative mass 1 unit. So the neutron with the symbol, the small n, has no charge. Remember earlier we said it was neutral. Its mass is almost identical to the proton, 1 unit. Now let's have a look at the electron. Symbol small e, relative charge -1, relative mass 1/1840 of a unit. So the electron, symbol small e, has the charge -1, opposite to the proton, which is +1. And its mass very, very small, almost negligible. It is 1/1840 compared to a proton. Proton number, Z, is the number of protons in an atom. Atoms of the same element will always have the same proton number. Proton number equals number of protons. 2. Since atoms are neutral, number of protons equals number of electrons. So remember this, the proton number, which is a very useful tool to a chemist because as you will see later, it helps us identify the location of an element in the periodic table, is basically the number of protons in the nucleus of an atom of an element. Now, because the proton number is the same as the electron number, proton number is also a guide that will help you identify the number of electrons in a neutral atom. Example A. There are 12 protons in a magnesium atom. Therefore, this atom has 12 electrons. The proton number of fluorine is 9. Therefore, this atom has 9 protons and 9 electrons. So remember, the proton number is the number of protons in the nucleus of an atom of an element. Nucleon number, symbol capital A, is the total number of protons and neutrons in an atom. Nucleon number equals number of protons plus number of neutrons. Example, the sodium atom has 11 protons and 12 neutrons. Therefore, the nucleon number of sodium is 23. So the nucleon number, this is another very important number because it will help us relate to the mass of an atom, which we will see later on in another lesson. This number, the nucleon number, is the protons added to the neutrons that are in the nucleus. Now, if I said we had 6 protons and 6 neutrons, this means the nucleon number will be 6 protons plus 6 neutrons, which is 12. Good. So remember, nucleon number is the proton number added to the neutron number. Another example, the nucleon number of lithium is 7. A lithium atom has 3 protons. Therefore, this atom has 4 neutrons. Symbol of elements. The nucleon number symbol is A. Proton number symbol Z. The X represents the symbol of element. Example 1. 3919 K. Element potassium. The nucleon number is 39. The proton number 19. Therefore, the number of protons is 19. The number of electrons will be the same, 19. The number of neutrons will be the nucleon number minus the proton number, which is 20. So this is looking at an element symbol. The element symbol gives us two pieces of key information, the nucleon number and the proton number. Let's jump up to the board and have a look at one or two of these symbols and then what information we can work out from it. Let's draw the symbol for carbon, which I mentioned earlier. Carbon symbol is C. It has a nucleon number of 12. We write the nucleon number up here. It has a proton number of 6, which we write just below here. So this is your nucleon number. Now, an easy trick that you can use is to just write down a very short form. Nuc equals P plus N. So remember, the nucleon number is equal to the proton number plus the neutron number. Now, if you know that this number is 12, you just put the 12 up there. This number is 6. You just put the 6 up there and you can find the unknown neutron. So an easy, simple way to always be able to work out proton number, neutron number and the nucleon number. Finally, don't forget proton number equals electron. So if your proton is 6, therefore your electron is also going to be 6. Example 2. A sodium atom has 11 protons and 12 neutrons. Write the symbol of sodium. So let's begin with this. We first want to write the symbol for sodium. So first, let's begin with sodium. We have the symbol, which is Na. The information given to us is we have 11 proton. So let's put that down here. 11 proton. We have 12 neutron. We need to write down the nucleon number and the proton number. Well, we know the proton number, so we can put that in immediately. That's 11. But up here, we have a problem. We need to work out the nucleon number. Remember the simple equation? Nuc equals P plus N. Your proton is 11, your nucleon is 12, so your nucleon number is going to be 23. So you just put that in here, like so, 23. And then, what about the electrons? Remember, the electron is the same as the proton. So, and you pretty much have all your angles covered and all the questions answered. So let's have a look at the slide again. Write the symbol for sodium. Well, it's Na2311. The proton number is 11. The nucleon number is 23. A sodium atom has 11 electrons. So try to remember, nucleon at the top, proton at the bottom. The symbol nuc equals P plus N. That will get you through most of the calculations that you need to do. And don't forget, proton equals electron. The electronic structure of an atom. Electrons are arranged in the shells of an atom. Each shell contains a certain number of electrons. For elements with proton number 1 to 20, first shell, maximum number of electrons 2. Second shell, maximum number of electrons 8. Third shell, maximum number of electrons 8. or 18. So this is very, very important to understand that the electrons are not all of them placed in one shell, or that they are arranged in a random way. The arrangement is quite fixed. The first shell can have a maximum of 2, the second shell a maximum of 8, and so on. So we need to know for our examinations and our chemistry lessons how these electrons are arranged and how we write down their arrangement. Remember, first shell, 2 electrons. We call this duplet. Second shell, 8 electrons. We call this octet. Third shell, 8 or 18 electrons. Complete the table below. Hydrogen has the following symbol, H. Right. Hydrogen has 1 proton. That's it. Which means it only has 1 electron. So if you were going to draw the atom of hydrogen, you would draw something like this. Okay, let's just rub this off because we need the space. So hydrogen, you draw a nucleus in, and then you draw the first shell, and it contains 1 electron. You can use an X symbol for the electron or just a dot. So this represents hydrogen. The symbol for hydrogen, 1, 1. The electron arrangement for hydrogen. Now, for short form, we'll just use the symbol EA. The electron arrangement is 1 because it only has 1 electron. Let's have a look at another one. Helium, symbol 4,2. Helium. So now we're looking at helium. Helium symbol is 4,2. It has 2 protons, which means 2 electrons. How do we draw this? Well, once again, we start with the nucleus and we draw in the first shell. We have 2 electrons. The first shell can take a maximum of 2. So we draw 1 electron in here and 1 electron in here. How do we write this electron arrangement? Just like that, 2. Let's move on and try a slightly more complicated one. Lithium, symbol 7,3. So now we've got lithium. So let's put lithium up here, 7,3, which means we have 3 protons, which means I have 3 electrons. We'll start by drawing the nucleus once again, the first shell. Now remember, the first shell can only take a maximum of 2 electrons. So we put 2 in, 1, 2. This leaves me with 1. This 1 electron must be placed in the next shell. So we draw in the second shell and we put that electron in there. Now when we do the electron arrangement, we need to specify the shells. So here I would say in the first shell I have 2, in the second shell I have 1. So I write the electron arrangement as 2, 1, which means we understand it's got 2 electrons in shell 1, 1 electron in the outer shell, which is the shell. 2 and 1 equals 3 electrons. I hope you're getting the idea. Let's try something a bit more complicated. Sodium, 2311. Right. Now we're looking at a quite large number of electrons. So let's do the sodium over here. Sodium, 2311, which means I'm looking at 11 electrons. Let's start. Draw the nucleus and the first shell. Remember, the first shell can only have 2. So if I put in 2 here and I subtract 2 from here, that means I'm left with 9 electrons. Now I go to the second shell. The second shell can have a maximum of 8. So if I put 8 here, I'm going to be left with 1. So let's put in the 8 first. 1, 2, 3, 4, 5, 6, 7, 8. So I've done the 8. I'm left with 1 electron. I go to the next shell and I put it in here. So altogether I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. How do I write this electron arrangement out? So the electron arrangement will be written as the inner shell first, 2, then the next shell, 8, and finally the outer shell, 1. So remember, start from the inside and work your way out. Fill the first shell. Whatever's left, start filling the second shell. If the second shell gets full, move on to the next shell. And that way you have shells being filled from the inside to the out. And when you write the electron arrangement, always begin with the first shell, then the next, and then the next, and then the next. So, if you have chlorine 3517, so how would we do this one's electron arrangement? So, remember what we've got? We've got chlorine 3517. So let's begin. 17. The first shell, we put 2. This leaves us 15. Next shell, we put in 1, 2, 3, 4, 5, 6, 7, 8. Subtract 8, we're left with 7. Go to the next shell. 1, 2, 3, 4, 5, 6, 7. How do we write the electron arrangement? Start in the inside, 2, 8, and in the outer shell, 7, like so. So I hope you understand. Always start from the inside and work your way to the outside. Valence electrons are the electrons in the outermost shell of an atom. The chemical property of an element depends on the number of valence electrons in the atom. Example, sodium has 1 valence electron. Chlorine has 7 valence electrons. So remember, valence is the outermost shell. And as we said, the outermost shell, the number of electrons in it is known as the valence number. Here, for lithium, we have 1 in the outermost shell. Here with sodium, we also had the same number, 1 in the outermost shell. As you'll see later, if elements have a similar number, it also means they have quite similar chemical properties. Over here, chlorine, outermost shell, 7. So it has a valence number of 7. Isotope. Atoms which have the same proton number but different nucleon number. Atoms which have the same number of protons but different number of neutrons. Isotopes have the same number of valence electrons. Therefore, they have the same chemical properties. Remember, an isotope has the same number of protons, which means it must have the same number of electrons. Therefore, the same electron arrangement. So when they have the same electron arrangement, they will have very similar chemical properties. Isotope have the same proton number. Therefore, they belong to the same element. Isotopes have different number of neutrons. Therefore, they have different atomic mass and different physical properties. So, an isotope usually has different physical properties because its mass is going to be slightly different due to these additional neutrons in the nucleus. Examples of isotopes. Hydrogen. Now we have three types of hydrogen. If you look at the slide, it says hydrogen 1,1, hydrogen 2,1, which we call deuterium, and hydrogen 3,1, which we call tritium. All of these are slightly different. So let's just clear this off. Now let's have a look at the symbols for the three types of hydrogen isotopes. Like I said, we have hydrogen 1,1. Now in hydrogen 1,1, proton equals 1, neutron equals 0. In hydrogen 2,1, the proton number is still 1. The neutron number is 1. And in the third hydrogen, 3,1, the proton is 1, the neutron is 2. Now let's clearly see the definition of isotope is same number of proton. The proton, the proton, the proton. All of them are the same. So the proton number is always the same, but the neutron number is different. Here I have 0, here 1, here 2. So the neutron number is different. So this is the main thing about an isotope. Same number of protons, but different number of neutrons. Chlorine. Chlorine 35, nucleon number 35, proton number 17, number of protons 17, number of electrons 17, number of neutrons 18. In chlorine 37, proton number 17, the same. Number of protons 17, the same. Number of electrons 17, the same. Number of neutrons 20, different. So the nucleon number and the neutron number are different, but the proton number and the electron number are the same. Oxygen. If you go through the chart on oxygen, you will find the same thing. The proton number 8 is the same for both the three isotopes of oxygen, but the neutron number is different for all three of them. Remember, isotope, same proton, different neutron. Question. Compare chlorine 35 and 37. Write down the similarities and differences between the two isotopes. So, think about the key things you need to do in this compare. We want to know the comparison for proton number. We want to know about the nucleon number or the neutron number. So let's put both of those in. We want to know about electrons. We want to know about the valence. If you can tell us, the valence is also very useful because it will tell us about chemical property. So let's do that one here. Chemical property. What about the physical property? Let's add that here as well. So all of these are the kind of things that you need to compare when you're doing this question. So go through it slowly. You're doing chlorine 35 and chlorine 37. Go through them and work out those things. Have you quickly made a jot down? Let's have a look at the answer. Isotope chlorine 35 and chlorine 37. Similarities. Same proton number. Same number of electrons. Same number of valence electrons. Same chemical properties. The differences. Different nucleon number. Different atomic mass. Different physical properties. Which of these atoms are isotope? Explain your answer. Look, when you're looking for an isotope, look for the proton numbers. Remember, the proton number must be the same. Or, if it's a neutral atom, the electron number must be the same. This is your key for identifying isotopes. And then why? Remember the statement. Same number of proton, different number of neutron. Have you done this question? Have you put them down? Let's check the answer. The answer, P and R, because the proton number is the same, but the nucleon number is different. Uses of isotopes. Nuclear energy, uranium-235, to produce nuclear energy. Hospital, cobalt-60, gamma rays, to sterilize surgical equipment to treat cancer. Iodine-131, to treat cancer of the thyroid glands. Sodium-24, to detect blood clot in the blood vessels, thrombosis. Agriculture. Phosphorus-32, to trace the rate of nutrient absorption in plants. Nitrogen-15, same use, to trace the rate of nutrient absorption in plants. Gamma rays, to sterilize pests, to inhibit sprouting of potatoes, onions, ginger. Industry, gamma rays, to check wear and tear in engines, to gauge, control the level of content in canned food. Strontium-90, to gauge, control the thickness of paper and metal in industries. Cobalt-60, to detect any cracks in a metal structure or concrete structure. Carbon dating. Carbon-14, to determine the age of an artifact in archaeology. So these are some of the uses of isotopes. It's very important that you do know them. It's a common question in examinations. What is the use of carbon-14? Carbon dating. What is the use of cobalt-60 in medicine to treat cancer? What is the use of iodine-131 in medicine to treat cancer of the thyroid glands? What is phosphorus-32 used for in agriculture? To measure absorption of nutrients in plants. So these are common things that always come out. So you really do need to know the use of each of the isotopes that we have mentioned. So remember the key things. The atomic model, Dalton, Thomson, Rutherford, Niels Bohr, and James Chadwick. Remember after that the subatomic particles, proton, neutron, electron. Know their characteristics. Remember the symbol for an element, the nucleon number, nuc equals P plus N. Proton number, which is the number of proton, also equal to the number of electrons. Finally, remember how to arrange the electrons in the shells. In a shell first, then the next, then the next. Remember the maximum number for each of these shells. And finally, what we've just done, the isotopes. Remember their function and remember their definition. Same number of proton, but different number of neutron or different nucleon number. That's all the time we have for this lesson. Thank you for watching iTTV.